Alrighty, hey guys, coming to you from my room down here in the big old city of West Lafayette, Indiana, if you can't already tell by all the Oliver crap. And like I promised, this is the video about the soil tests I took, and it's not pretty. I kind of expected them to be pretty bad, but I wasn't expecting them to be this bad. This first one is a field that I actually took the video of pulling samples in, and it's the one that I took the video of finishing up chisel plowing, where there's a heck of a hard pan in it. So I guess I'll just start from this side and work my way over. So this is the organic matter, which as far as making fertilizer recs doesn't really mean a whole lot with the tri-state fertilizer recommendations. This is the percent, or the parts per million of phosphorus, which these are the worst numbers on the whole paper. For corn and soybean, with the tri-state fertilizer recommendation, your critical level is going to be 15. So all these should be 15. And these are parts per million. The way you convert this to pounds per acre is 1 acre furrow slice of soil, which is 1 acre of soil 8 inches deep, is 2 million pounds. So to convert parts per million to pounds per acre, all you do is take this number times 2. So basically what this is telling me is that in 1 acre of soil, I only have 6 pounds of phosphorus in that field, 12 pounds in that field, and 18 pounds in that field, where you at least want 30 pounds. So that's bad. For K, or for potassium, or K, you actually have to come in and use the tri-state fertilizer recommendations to calculate your critical level. And I guess I should tell you what the critical level is. To any of you guys outside of Michigan, Indiana, or Ohio, really these equations aren't going to mean jack to you, because every region uses their own. The tri-state is just what Michigan, Indiana, and Ohio have decided to base their fertilizer calculations on for all the soil labs and all the ag colleges in those 3 states. But basically, for what I'm doing here, this is your graph to determine which equation you need to use to calculate your fertilizer. This line here is your critical level, which for corn and soybeans with phosphorus, this is going to be 15. So if you're between 0 and 15 ppm, you have to use what's called a buildup equation. This next dotted line here is the maintenance limit, which for corn, soybean, and phosphorus is going to be 30. If your parts per million is between 15 and 30, you use what's called a maintenance equation. And then if your soil test level is above 30 ppm, you use what's called a drawdown equation, which is basically applying enough fertilizer for crop removal, but in a year like this where grain prices are bad, but you still have really high soil test levels, it's basically allowing you to apply a little bit of fertilizer, but draw your soil test down to the maintenance limit. So basically, this is if you're looking to save a little money and you have the soil test levels to allow you to put on reduced amounts of fertilizer. Now, for wheat and alfalfa, your critical level is going to be 25. Your maintenance limit is going to be 40. And what you have, or what we call the drawdown limit, is going to either be 40 or 50 respectively, whether you're corn, soybean, or wheat. So as far as K goes, to calculate your critical level, it's 75 plus 2.5 times the CEC, which stands for cation exchange capacity. Basically, soil soil particles themselves are negatively charged, which means they bond to positively charged cations. The fertilizer, or the phosphorus and potassium fertilizers we use, which for phosphorus the fertilizer we apply is in the form of P2O5. For potassium, the fertilizer we apply is in the form of K2O. Where was I going with this? Oh yeah. So since soil is negatively charged, it bonds tightly to cations. Phosphorus and potassium both have a positive charge, so they bond tightly to soil. Nitrogen, if you put it on in the form of ammonia, which is what anhydrous is, it has a positive charge, and it will bond to soil. However, ammonia is not plant available. It has to go through a nitrification process to allow it to become plant available, and through that it loses the positive charge, and nitrogen leaches. Once it loses that charge, it will leach through the soil very easily, which is why very few guys put on all their nitrogen pre-plant, because you're taking a big risk that if we get a lot of water like we did this year, there's not going to be any nitrogen left in the ground when the plant needs it, because it's all going to leach out during a heavy rain event. So that's why I side dress, is because we usually have a fairly wet spring and early summer up there, and if I didn't side dress, I would most likely lose all my nitrogen. But anyway, back to what I was with the fertilizer calculations. So for K, what I had to do is come in here and I had to calculate my critical level, which is this line here. And basically what I did was made an equation in Excel so that I could repeat it through all these when I go through and put in the rest of my fields. But it's 75 plus 2.5 times the CEC, which is cation exchange capacity, and for this particular field, cation exchange capacity was 7. So you do all that math, and I get a critical level of 92.5. Now, on these soil test levels, my soil test level for potassium on that field was 105. So, of everything, that is the only field that is above the critical level. So for that one, for my K recommendation, I could just do basically what's a straight rate for maintenance, which is yield potential times crop removal. And for crop removal, basically what you do is you use a constant that they have come up with based on experiments and stuff like that, which you got to come down here to this chart, go to corn, grain. For K2O, constant is 0.27. And for P2O5, same thing, you got to use a constant, which is 0.37. Now, as far as my phosphorus recommendation on this field, obviously at 9 ppm I'm way below the critical level, so I had to use a buildup equation, which is this big long thing, which is the critical level 15 minus the soil test level, which for that field would be 9, times 5, plus yield potential times crop removal. Now in this case, yield potential is whatever you make it. I'm going to fertilize for 200 bushel corn and 60 bushel beans. K2O, you have a similar equation, it's just a lot longer. Same thing, critical level times soil or minus soil test level times 1 plus 0.05 times the cation exchange capacity, and then all that plus yield potential times crop removal plus 20, which is another constant, and I'm trying to remember. I'm trying to remember what the heck the 20 is for, but I can't remember. But basically that 20 comes from more experimentation. We know we need to add another 20 pounds just to be on the safe side to get this equation to work out correctly. So that's kind of brief run through of how you got to calculate your fertilizer Rex, and that's not pounds of product to apply, that's just the pounds of P and K you have to apply. Pounds of product is actually going to be more, because if I'm applying DAP, which is 1846.0, and potash, which is 0060, which those numbers are N, P, and K content. So DAP is going to be 18% nitrogen, 46% phosphorus, no potassium, and then potash 0060 is going to be 0 N, 0 phosphorus, 60% potassium. And since they're not 100% nutrient, I'm going to have to apply even more product to get to my 104 pounds of P and my 74 pounds of K. But just kind of back to looking at the soil test itself, these phosphorus levels are, I have never ever seen soil test levels this low for phosphorus. This is bad. K, the 105 is not terrible, but the 83 and the 60 are, again, those are, ugh. I hope I never see numbers this low again. I mean, I've pulled soil tests on ground that I've pulled out of conservation that haven't been this low. So this tells you how good these fields were taken care of before I got a hold of them. Magnesium doesn't mean a whole lot, because that's not a macronutrient, that's a micronutrient. And either way, these are all really high. Calcium, again, doesn't mean a whole lot in terms of plant growth, because it's a micronutrient. The only thing about this is that the higher your calcium content, the more likely the field is to resist a pH change, which in this case they're low, so it's not going to resist pH change that great. The pHs are surprisingly not that bad. For corn and soybean, you want about 6.5. So that field's right dead nuts. That one's close, and this is 7.2. So this field actually needs acidified, which you can do that one of two ways. Either anytime you add nitrogen to a field, you're going to acidify it, and the product that we actually use specifically for acidifying soil is sulfur. But for how far off that is, for how far off that is, it's really not worth it, because that's probably going to change here over the next year. And then we actually have two different ways of calculating soil pH. There's the Bray P1 test and there's the Malick 3 test. And they'll both get you to about the same thing. The only difference is the extracting solution that the two tests use. And one is good for a certain soil type and one is good for another soil type, but my soils test where we did that in lab, or my soil class we did that in lab, was 2 years ago, and I'd have to go back through and look at the book to see which one's better for which. CEC is about average. But one note, usually the higher your organic matter, the higher your cation exchange capacity is going to be. Because organic matter is very positively charged. And basically, the higher your cation exchange capacity, the tighter the soil will bond to cations, which can be a good thing and it can be a bad thing, because the tighter it bonds to them, the harder it is for the nutrients to go into soil solution and become plant available. But it also means that it has a higher capacity for holding nutrients on the flip side. So like I say, could be a good thing, could be a bad thing. In a dry year, that's where you run into issues. In a year with normal rainfall, it doesn't really affect you a whole lot. But it is better to have a high CEC. That way you can put more nutrients into the soil and it'll hold on to it for multiple years. And this is just percent base saturation, which is not really important to, again, not really important to calculating FertRex. So, yeah, I hope some of this jabbering made sense. Like I say, if you're not from Michigan, Indiana, or Ohio, these equations aren't really going to do you a whole lot of good, because every region has their own soil testing and fertilizer recommendation system. So like Iowa's going to be different, Louisiana will be different, Maine will be different. It just depends on your region. So the best thing to do if you want to do your own fertilizer recommendations is find the nearest either university with an ag program or a soil test lab or something like that, and they should be able to tell you what equations you need to use and stuff like that. And if you want to do the lazy man's way out, there are just straight rates you can apply for P and K, but like for this, you can tell they haven't updated these in a while because it only goes up to 180 bushel corn. Now we're making 250 bushel corn, so these things don't really do you a whole lot of good. So, but there is that option. So, yeah, I hope you guys can make heads or tails of this. I'm sure it was probably confusing because I took an entire course on soil nutrient management, and I just explained it to you in probably 15 minutes. So, but yeah, that's where I'm at right now. So, I guess we will catch you guys on the next one.